So I'm very happy to present today Dr. Rebecca Pullon. So she graduated with a degree in biomedical engineering from Auckland about 8 years ago, I believe, 2010. She then went on to Oxford, where she completed a DPhil in biomedical engineering, working in mobile health. So part of her work was looking at and analyzing, measuring and analyzing vital signs during pregnancy. And that's what she's going to be talking to us today. So she moved back to New Zealand about a year ago, and so now she is a research associate in the Department of Anaesthesiology at FMHS, but she is based in Hamilton, working at the Waikato Clinical Center, where she is working on monitoring EEG during operations. But she's going to talk to us about her PhD work, looking at vital sign monitoring during pregnancy.
Cool, thank you. Can everyone see me if I stand on this side? Is that all right? Cool, okay. So every day, thousands of women give birth to a child. Yet 15% of these women will develop some sort of complication in pregnancy that will have long-lasting effects for them. Things like gestational hypertension, high blood pressure in pregnancy, preeclampsia, sepsis or severe infection, hemorrhaging, or gestational diabetes. And the best way to kind of reduce the severity of these complications is to detect them and treat them early. And one way that we can do that is by physiological modelling using something like an early warning score system. So this is a typical early warning score chart, which is used in hospitals. So when people are admitted to a hospital, their vital signs will be recorded, usually 4 hourly, on a chart like this. So your vital signs are down the left-hand side, time is across the x-axis, we've got our range of normal is the white, and then yellow is slightly abnormal and red is very abnormal. The problem with these charts is that there are several of them. Each chart looks different, has a different number of colours, or it may be that they use numbers to kind of indicate the extreme abnormal physiology. And they all have different thresholds. So to illustrate this, here are 8 different early warning score charts of systolic blood pressure and diastolic blood pressure. And you can see that some of them have kind of 2 colours, just a yellow and a red. Some of them also have an orange segment in the middle. The thresholds are all slightly different. 2 of the charts don't consider diastolic blood pressure important to be measuring in the early warning score. And so kind of the challenge is, well, actually what does happen to a woman's vital signs during pregnancy, and how can we actually have an evidence-based chart that would capture those changes. So the way that these charts are kind of come up with at the moment is usually a bunch of clinicians get together and kind of decide from their experience what they consider to be abnormal physiology. So what I'm going to talk about today is a proposal of new evidence-based hospital charts. So this is, as Vinod mentioned, the work that I did when I was doing my PhD in Oxford, and I finished about a year ago. So we designed an observational clinical trial which collected vital sign information during pregnancy and after delivery, and it's from this information that we've kind of proposed a new obstetric early warning score tool that is specific to the stage of pregnancy. Cool. So a little bit about the study. It's called the 4P study. 4P stands for Predicting Physiological Patterns in Pregnancy. So we recruited women around about 12 weeks of gestation, usually at their first dating scan. We monitored their vital signs once a month during pregnancy. Usually a midwife would perform a home visit. And then at delivery, we would give them a home monitoring kit. So that would be made up of all of this equipment except for the mobile phone, because a woman could not measure their own respiratory rate. And we'd ask the women to measure their own vital signs once a day for 14 days after delivery, so that we could also capture the postnatal data. So there are 3 sites in the UK that contributed data to this: Oxford, London and Newcastle, and it started in August 2012, and data collection finished in September 2017 with 1,000 participants. But I'm going to talk about the section of the data that I used for my PhD, which was up until July 2016. So by then we had 620 women on the trial, and this is how much data we had in the antenatal, so during pregnancy in the top graph, and postnatal after delivery in the bottom graph. So because of the home monitoring phase after delivery, there's a lot more data in the 14 days after delivery, but a lot of that self-monitored rather than by a midwife who we consider an expert in this situation. So the first thing we need to do is make sure that we have good quality data. Respiratory rate is currently the only vital sign which is not routinely measured using an electronic device. So we wanted to see if we could get an electronic measurement of respiratory rate. And to do this, we use the pulse oximeter, which measures your blood flow through the extremities, usually the finger, and the inbuilt accelerometer and gyroscope in a mobile phone. So your breathing modulates heart rate in a few different ways, which we can measure through the pulse oximeter signal. It modulates the actual heart rate, it modulates the baseline wander, and it modulates the amplitude. So you can derive 3 respiratory signals from a PPG signal, which I've kind of illustrated here. As well as these 3 signals, we took the principal component of those 3 to kind of extract the dominant respiratory signal, and also kind of performed analyses on that as well. So we essentially had 4 signals from the pulse oximeter. Then did a similar thing with the accelerometer and gyroscope from the mobile phone. So these are triaxial. The mobile phone was just resting on the woman's chest as she was reclining around about 45 degrees. And we'd measure that for 1 minute. And the signal looks something like this. This is the y-axis of the gyroscope, and you can see the vertical lines are heart rate, and so often in the gyroscope you would be able to see heart rate information, but once you filtered that you could get a very clear respiratory signal from the actual movement or rotation in the case of the gyroscope. So then we used a few different methods to extract respiratory rate, such as peak detection in the time domain, the Fourier transform, and AR models. We can do this both for the pulse oximetry signals and the gyroscope and accelerometer signals. You can kind of see for this example, there's a very clear dominant respiratory rate at around about 9 breaths per minute, 9 or 10. So we did that for just under 700 of these traces. And this is, essentially the thing to get from this graph is that the principal components, which are every 4th one, so AP, GP, and PC, had a lower median, this is absolute error in respirations per minute, had a lower median error than the components that made them up. And the one with the lowest error, I think, was actually this gyroscope signal here. Yeah. Some of these signals were of poor quality, and so we also came up with a respiratory quality index using dynamic time warping of each beat individually in order to remove poor quality signals. And unsurprisingly, as you remove these poor quality signals, your absolute error decreases, so you get a much better measurement of respiratory rate. So then it's a trade-off between actually how many of these records are you actually including in your analysis as to what the quality of them is. There were some limitations of the reference rate that we used. So when the midwives were measuring respiratory rate at the same time that we were getting the 60 seconds of data from the pulse oximeter and the accelerometer, they would also tap the screen of the tablet once per respiratory signal, so usually as the person was breathing in. You can see these are 3 examples of the taps being the orange vertical lines over top of the accelerometer signal in this case, where the midwives weren't quite right. So in this top one, you can see there's a breath missing here that you can see in the accelerometer, and here and here. So there's just a few missed breaths, but the difference between 18 rests per minute and 21. In the second trace, the midwife is completely forgotten in the first 30 seconds and then tried to catch up. And in the last one, it's just very noisy that you can't see any underlying respiration in the accelerometer signal, and the taps are very uneven. So it's hard to tell what the true respiratory rate was in this case. So in conclusion of this respiratory rate part, generally respiratory estimates from the gyroscope had lower errors than the accelerometer, so they were more reliable. Principal component waveforms were of better quality than the three that made them up, as I pointed out before. But ultimately, they are actually quite close, so it probably would come down to pragmatic choices as to which one you would choose to use for an electronic measurement of respiratory rate, so cost and availability. But perhaps if you had both, then fusing the results could improve the respiratory estimate even more. So once we have reliable vital sign measurements for all of the vital signs, so by vital signs I mean heart rate, oxygen saturation, blood pressure, temperature, and respiratory rate. We can then see what actually happens to them over time. So over time during pregnancy and then after delivery. So in order to do this, we used a multi-level model or a hierarchical model. So this is, by the name, has multiple levels, which is therefore appropriate for a longitudinal modelling. So where you have one patient who's contributing several data points over time, is more likely, their data points are more likely to be correlated to each other than they are with someone else's. So you've kind of got these two levels to the data. So that means you've got two sets of parameters, your population effects and the individual effects. And so you can model at both levels. To kind of illustrate a little bit more about what this means, say we've got 3 participants here, orange, purple and green, and they're all contributing a different number of recordings at various time points. These are the individual errors for this orange participant, so their parameter in the middle is here, so that's B1, and then they have individual errors to their individual measurements. The green person is here, and so their individual subject-specific parameter is Bn, and similarly with B2, and then we've got our overall population model, which is beta. And so we have used a linear model here, so we're assuming Gaussian distributions of within each patient's vital sign measurements. We considered a few shape trajectories, so standard polynomials, fractional polynomials and cubic splines, and ultimately found that standard polynomials were adequate enough to represent the data. We treated the antenatal and postnatal data separately, and I solved it using the software called STAN. So here is what that all looks like. In the left-hand column, we've got the antenatal data, so during gestation. In the right-hand column, we've got the 2 weeks after delivery. And then each vital sign, so systolic blood pressure, diastolic blood pressure, heart rate, temperature, oxygen saturation, and respiratory rate. So what to take from this, it is often been said that blood pressure has a dip in mid-pregnancy, and so here we are seeing a slight dip in both in diastolic blood pressure and systolic blood pressure, but it's not actually as pronounced as it is often thought to be. It's actually about 1.5 millimeters of mercury from 12 weeks to about 20, where the minimum is. So probably actually not that clinically significant to need to worry about. Heart rate goes up during pregnancy, so from about 80 to about 90, so 10 beats per minute may be the change within a threshold in our early warning score system, so we probably do need to worry about the changes in heart rate during pregnancy. Temperature decreases only very slightly, not really clinically significant. Oxygen saturation we also found decreased during pregnancy, and this hasn't been recorded before, so this is new information. As to whether that will impact clinical practice, probably not, because we still want people to be generally over 93% saturated anyway. Yeah, and then there is no change in respiratory rate during pregnancy or after delivery. So this is our population level trends. Yeah, and we can compare that to literature. So we had done a systematic review of vital sign data, so pooling all of the existing information together and modelled it in a similar way. And so here we're comparing this 4P data that I've just shown you, which is the purple line, with our results from our systematic review, which is the green line. So we've found that this 4P data shows that blood pressure and heart rate is higher than it has been reported previously in literature. We think that the reason for this is that a lot of the existing data is quite old, so it's usually 20 to 30 years old, and they're quite small studies with large variation which have been pulled together. As well as that, our techniques for measuring vital signs have been updated, and so that probably accounts for the changes that we're seeing here, but interesting nonetheless. So we can also look at individual subjects' trajectories. So this is systolic blood pressure. On the left here is our distribution of likelihoods for each of those subject-specific parameters that I pointed out before. So if we take the most likely parameters, these are the blue in the middle, so around 0 of our, around 0. And on the right-hand side, this is what that trajectory looks like over time, and so that is closely following our mean trend. If we then take our most unlikely parameters, they are in red, so kind of spread around the outside here. We see that in this case they are all high blood pressure. They also may be low, but in this case they're all high and they're kind of at the extremes. But does this actually follow what the individual data points are? Well, here are 3 individual patients and their trajectories for systolic blood pressure, and we see that there is some variation, but this red line, which is the subject-specific trajectory as opposed to the population mean in black, does tend to follow their data quite closely, particularly if you look at this last one. So that allows us to model on both levels. We can also look at other factors such as parity. So parity is the number of live births greater than 20 weeks previously. So nulliparous women are women who have not had any children before versus multiparous, 1 or more. We see that there is the nulliparous women have a slightly elevated blood pressure and heart rate compared to the multiparous women, but again, it's just like that dip we saw in mid-pregnancy. It is very small, so probably not clinically significant. We can also look at something like BMI. And so here I've included a quadratic term for BMI as well as the interaction of BMI with gestational age. Of note here is in systolic and diastolic blood pressure at the beginning of pregnancy, so around 10 weeks, which is where we started measuring. It's more spread out. These groups are more spread out, but then as we go over time, they kind of tend to be closer together. So they're all ending up towards the same point. Whereas the opposite occurs in heart rate. We see them spread out over time. Cool, so now that we've looked at our models, let's try and put them into an obstetric early warning score system that's specific to this stage of gestation. So on the left here, we've got our existing Oxford chart, which is what I'm going to be comparing to. So this is what is used currently in the Oxfordshire hospitals, and they don't change over time. So for this illustration, we're going to assume that we want to identify the abnormal physiology. So right at the bounds of where abnormal physiology is defined as the bounds of normal physiology. So we're going to look at the outer centiles of those models that I've just shown. So at one end, the first percent, 5% and 10%, and at the other end, 90, 95 and 99. So this is what the first 3 vital signs look like. And here we've separated it into antenatal and postnatal and have a time axis compared to this Oxford chart. So immediately you can see that the bounds of this new chart are much narrower. So these red parts are from 90 to 145 here, and 90 to 160 on the existing Oxford chart. Yeah, and the biggest difference is in just diastolic blood pressure. And this is for the last 3 vital signs, so temperature, oxygen saturation, and respiratory rate. Again, a high respiratory rate is quite different. So from our data, indicated that anything that 25 rests per minute and above was considered quite abnormal in the outer 1% of the population, whereas you needed to get to rests of 30 on the previous Oxford chart in order to be considered abnormal. So what difference might this make with a patient? Well, here's an example patient. This is using the postnatal chart after delivery. This patient had a forceps delivery, and they were doing fine until about 6 days after delivery when they were discharged. And then they came back in again at 11 days and probably had endometritis, that's the right word. Yeah, so if we look at the left-hand side, this is our existing Oxford Early Warning Score system, and the blue dots are the vital signs. So there are the 6 of them, and at the bottom here I've added those up. So I've assigned a 1 to the yellow and a 3 to the red, and we get this kind of trajectory that seems to be mainly at 0. For our new proposed charts, again the same vital signs, different charts. I've assigned a 1 to the yellow, 2 to the orange, and 3 to the red, and added them up here, and we see that here it is really 0. It's hard to know whether this would have actually made a difference in clinical practice, but potentially by seeing that actually there was some indication that her physiology was abnormal, maybe she wouldn't have been sent home at day 6 and they would have picked it up earlier. Hard to know, but there isn't, we're showing that we are picking up some changes in physiology. So to kind of conclude this section, what I've shown you has confirmed our existing knowledge in pregnancy about systolic and diastolic blood pressure and heart rate trends during pregnancy. Gives us new information about how a woman's body recovers after delivery. So there has previously been very limited postnatal vital sign data. And it has allowed the creation of a hospital chart that is specific to the stage of gestation. But of course, further validation is required, and there's still a way to go until a system like this can be actually implemented in clinical care. One of the limitations of what I presented so far is that we've only considered each vital sign individually. And we've also used a discrete scoring system, so it's either a 1, a 2, or a 3, or a yellow, an orange, or a red. To finish off with, I'm just going to briefly talk about what it might look like to put these into a multivariate model. So what if we considered that our vital signs is like a 5-dimensional structure rather than just lots of 1D things that we're adding together. So in order to kind of illustrate this, we've just looked at the antenatal data, and I've excluded oxygen saturation because it's a one-sided distribution, and that is a bit tricky. So I'll come back to it another time. So here I'm showing bivariate distributions. So each pair of vital signs. The straight lines are from the univariate models that we saw just before, and the circle is from our bivariate distribution. So this is now a bivariate Gaussian distribution, so imagine like a hill where we're taking the ring around it, which is our 98th percentile now, rather than 1 and 99. So you can see there's actually not much correlation between these vital signs. Understandably, systolic and diastolic blood pressure is quite highly correlated, and the only other one that seems to have much correlation is diastolic blood pressure and heart rate. Yeah, the rest are quite small. But anyway, we will continue on with this despite that. So yeah, our other limitation was using a discrete score. So now we're going to look at what it might look like to have a continuous score to kind of measure our abnormal physiology on. So we're also reducing those 5 dimensions into a single number, which is a lot more manageable, particularly for clinicians. So we're normalizing our likelihood and then taking the log in this case. So, and I've called that a Z-score. So this is our Z-score on the y-axis, and we've got our gestational age across here. And so you can see that most of where 0 is very normal, and then a high number becomes more abnormal. So you can see that most of the data is within this kind of 0 to 3 range, which is a similar scale to what we had before in our univariate models. So we can compare the two. This is the univariate model that I presented before, and that's the aggregate score. So that's counting them up with where the yellow is 1, the orange is 2, and the red is 3. And this is our new Z-score that is being compressed from 5 dimensions. And we see we've got pretty good correlation. But where we have a discrete score in this axis, we've actually got a spread of scores in our y-axis, but we still see that same trend. So that looks promising. Let's take a specific set of vital signs. So here we've got diastolic blood pressure and heart rate, so the 2 vital signs which were somewhat correlated. And the X's here are 2 example measurements that you might have. So the first one is 90 beats per minute heart rate and about 95 diastolic blood pressure. So they would score a 0 in heart rate because it's right in the middle, right in the normal zone, but they would score a 3 in diastolic blood pressure. So their overall aggregate score would be 3. This other measurement here, we've got a heart rate of about 115 and a diastolic blood pressure of about 90. And so for this score, both of them are in the red zone, so they would score 6. If we look at these same 2 points on our multivariate model, which now I'm just showing the 2 dimensions of these 2 vital signs, we see that actually they are exactly the same distance from the centre, and so they would get exactly the same score because their likelihood is the same. Yeah, so translating that into clinical practice is quite tricky, and we don't yet know if that actually holds any clinical significance, but yeah, I guess it illustrates the point that if we're looking at things in multiple dimensions, we can look at how something is less likely to occur with that, the correlation between those 2 rather than looking at 2 vital signs individually. So yeah. Cool, so in summary, what I've talked about today, our motivation for doing this project is that about 15% of women develop complications in pregnancy. It would be good to detect these early. Current hospital charts are inconsistent in the thresholds that they have for vital sign monitoring and in how they add up the scores in order to escalate a clinical response. I helped run the 4P study, which is an observational observational clinical trial collecting vital signs from 1,000 women across 3 centres in the UK. And kind of after checking data quality, developing this respiratory rate estimate, we can model population trends in this data and then propose new hospital charts that could be used to monitor pregnant women. So yeah, thank you.
Thank you, Rebecca. So we have time for questions. Any questions for Andrew?
Thanks, Rebecca. Really interesting work. Your scoring system assumes or makes no assumptions, I guess, about which of those vital signs might be the most important.
Correct.
Comment on that and how you might change the scoring to account for that?
I think that's one of the reasons why I was keen to explore this kind of multivariate option, because then you're letting the data speak for what's actually important and which combinations of vital signs are more or less likely to be there. Yeah, I don't know quite how you would change the existing kind of univariate system to weight vital signs more importantly. I think the reason they are vital signs is because currently they are all considered to be vital. But if I had to suggest something, probably taking out one of the blood pressures, since they are highly correlated.
Which of those signs are more highly correlated with complications?
But all of them, it depends what complication you're looking at. Yeah. So respiratory rate is often the first thing to change, but often the thing that's less measured. Blood pressure often has the most severe consequences because you get preeclampsia from that. But yeah, raise a sign of infection.
Related here. Were there any fatalities in all those?
Any what, sorry?
Fatalities. Deaths of either mother or infant.
I think there was one death of an infant.
That doesn't give you much of a basis to.
Yeah, so the
most vital of the vital signs.
No. So this, like, the point of this data set wasn't to kind of say, okay, these people have developed complications, we're going to train our model to detect that. It was more to look at actually what is normal physiology, and can we infer something about what is abnormal from, well, where we think people should fall in experiencing a normal pregnancy or a typical pregnancy, I guess. Yeah.
David?
Yeah, so moving on from the outcomes, I'm interested in the process. Was there any thought given to the time of day that the recordings were taken? We know that there is change circadian.
Yeah, there was a little bit of thought given to that, and we recorded that. In like initial analyses, didn't find any differences in the time of day, partly because they were always awake. So I think typically you see a circadian rhythm if you're measuring vital signs when they're sleeping, but they weren't. So even if they were measuring them at midnight, they were still awake. So I didn't see much change was the answer to that. So I haven't pursued that more, but there will be something they will probably look into again.
Very interesting. And coming back to the outcomes, because, I mean, how do you see that this type of a study could help on preventing or detecting adverse events in outcomes in underdeveloped countries, where you have more problems and complications, but at the same time, it will be difficult to have these measurements for all pregnancies. This rich data in some underdeveloped countries. I mean, it would be impossible to have all of these vital signs.
Yep, that's very true. I think one potential about mobile health systems is that they are getting cheaper and are getting better in terms of like how far they can send data. So there's the potential to be able to perform all these vital sign measurements from a mobile phone. In which case it may become accessible in order to be able to do that in developing countries in very rural areas, particularly I'm thinking of. But yeah, I think we're a long way from that still, unfortunately.
Can I get back to the theme of disease specific, because we've tended to put blood pressure up as being a problem. You mentioned preeclampsia, but what about circulatory collapse and septic shock, when in fact the blood pressure will go down? So they really are red at the top and the bottom, aren't there, in some of these parameters?
Yes. Yeah. So I think.
How did they deal with that?
You mean how should they deal with that
How would this system of an early warning score deal with that?
So in the way I've approached it in this presentation by looking at our outer centiles, you would pick up both low and high blood pressure, and if we look at that woman, the example that I showed, we see that actually where she gets most of her scores from is low diastolic blood pressure. That is the biggest difference between this side and this side, is that she's triggering that response there. And I think one thing that this database will show is that we need to have like pregnancy-specific thresholds for things like sepsis. And to understand also how, like, what happens after delivery. So often sepsis comes postnatally for women, but there's not a lot of data as to actually how your vital signs should recover after delivery. And so understanding that, particularly the first 24 hours, I think is really key to addressing those problems.
I was just curious, on your proposed model there, and you've got the different colours, and you said
Yeah.
you've determined that by 95.
Yes.
Type thing. Were those numbers, those values that you've put the cut-off line at, is that the actual values that it becomes dangerous, or is that just what's normal or abnormal?
That's just what's normal or abnormal.
Okay.
So there we're making an assumption that we're wanting to know about the most abnormal physiology.
Okay, so it might not necessarily.
We haven't shown any, at the moment we don't know the outcome data associated with that. So we haven't shown that link yet.
So I've got a quick technical thing, but it leads on to the other question. It was around oxygen saturation.
Yeah.
Can you just explain to me what you meant about one-sided? And then secondly, I saw that it went down, I guess, during pregnancy, but it didn't seem to recover at all during the first 2 weeks. You said maybe it wasn't a big drop. But
Depends what you consider a normal person's oxygen saturation to be.
I guess I was under the impression that you were measuring the variation about normal with these graphs. So no, I don't, there it was there. So the middle two graphs on the right, dead centre and right-hand side.
So I would suggest from this data that 96% oxygen saturation is actually the average in a normal, healthy adult. And that actually at the beginning of pregnancy, your oxygen saturation goes up.
Right at the very beginning. Okay.
But the mechanism by which that occurs is currently unknown. What I meant by a one-sided distribution is that oxygen saturation of 100 is good. So we don't need to have an upper threshold there. So we're kind of only interested in one tail. So,
It's not poisonous to have too much oxygen in your blood?
no, it's quite okay.
More than 100% would be a problem.
I can see
But
Dennis
it's
is.
not measuring amount of oxygen, and I don't understand why saturation is always used if you don't know what the hematocrit is. So you don't know how much oxygen is being carried. So I was pleased to see it dropped in the final super analysis you did.
Yeah.
You don't think it's a vital sign?
I think it's almost a worthless sign.
There's a lot of emphasis on it in theatre environments.
Yeah, but it ain't worth much. If I'm right and all those other people are wrong.
Yeah.
Cool. Chris?
Your bounds are considerably tighter than the current charts.
Yes.
Did you get any sort of positive or negative comment from clinicians on that?
So the one hesitation with that is that you'll get too many false positives. And that is something that the validation phase of the study will need to look at very carefully. So yeah, that is a concern.
So kind of, I guess, just relating back to some of those questions then. So did you look at how many cases of complicated pregnancies you had here? So did you have people with pre-eclampsia or some other conditions? And did you look at some kind of validation like that? Whether your scoring system would have picked those up?
Not really is the answer. So I think there are about 10 people that developed preeclampsia. Not many that developed gestational diabetes. Yeah, I don't know the exact figures, but they weren't huge. So it wasn't kind of enough to be able to power an investigation into that.
But on the flip side, that probably means what you've got is maybe a good representation of what normal is.
Yeah, that's what we were hoping.
Right,
Yeah,
okay.
without being like extremely normal. Yeah, some other studies look at.
So just a quick question about the numbers and the cutoff points.
Yeah.
How did you decide where the normal physiology versus the abnormal one is? Because obviously in the normal charts, you know, they don't take into account the gestational time, but in yours, you're taking it based on the data that you analyzed, and you assume that most of them are normal.
Yes, so it's based on the outer centiles of the population that we had. So the model that I used assumed a Gaussian distribution, and so we took kind of the outer 1%, or 2%, 1% on each side for the very red. That number is a little bit arbitrary, but we were assuming that we wanted to know about those 2%. And then kind of the middle part is our normal is 80%, because that has been, so I took these numbers from a paper that had been published before that had done this analysis, so I am not actually 100% sure where they got it from.
That assumption could be challenged by...
It definitely could be, and I think when you're validating a tool like this, so when you have outcomes to measure it against, that is something that would probably be adjusted. Yep, definitely. Yeah.
So I might have missed it at the beginning, I'm sorry, but did you have any idea as to how these Oxford charts were created? Were they created based upon the same idea of just variation about normal, or were they created based upon dangerous events? That's the key difference.
Yeah, so they weren't based on data. I don't know exactly how they were created, but a typical theme with many of the early warning score systems is that it's usually a bunch of clinicians together in a room who kind of discuss and from their experience in clinical practice kind of decide what they think is abnormal. And each bunch of clinicians has a different idea as to what is abnormal. And by the population they're dealing with, and so that was kind of one of the main motivations for wanting to actually do an observational study to actually see what the data said.
But if there's a large degree of dangerousness, I guess, that has been brought into the Oxford charts, perhaps the clinicians actually use them in that sense, or do you just think they are looking for variations about normal?
I think they are only picking up the very extreme cases. And are potentially not aware of actually people who are early stages of developing complications. Yeah.
I was wondering whether you've been part of the ministry's work, because the Ministry of Health and Health Quality and Safety New Zealand are actually rolling out maternity early warning charts now. And they've done a lot of work both on the content of the chart, but interestingly on the colour, because different people respond to different colours in terms of alerts, and for reasons I don't really know, but they've not used red on the chart. But have you been part of that work, because it's going live in New Zealand?
Yeah, shortly? I have heard about it, but no, I have not been part of it. No.
It strikes me that your bullseye form, I guess, that you developed would be really easy for, may I say, even clinicians to understand. That seems
do you mean that
good direction to go.
Yeah, that's something that you would need an electronic early warning score system in order to be able to implement. So I think until hospitals have moved to recording electronic vital signs, even on the wards, that's not something you could implement. But I know, I'm hopeful that it would. I think this is a better representation of actually the landscape of what is normal and abnormal.
That's because you only found one correlation apart from systolic and diastolic blood pressure, right? If you had multiple correlations, then the two-dimensional thing wouldn't be sufficient.
I think the other, this is just a 2D representation of the 5D model, but I think the other way around. So the fact that I didn't find many correlations means that actually a univariate is probably adequate, because there isn't much interaction between the vital signs. But if there was more interaction, then I think there would be more of a motivation in order to implement a multivariate version.
number, and if that number is in the right range, everything is okay, and if it's not, what do they do then? Because that number would be influenced by lots of different vital signs that could point to different consequences.
Yeah, I think that the number itself could fit into the existing system that like early warning score systems trigger. So when you score 2 reds on the current early warning score chart in Oxford, for example, it escalates a clinical response. So the nurse at the bedside has to ring the clinical team who will come and review the patient. So like that system of track and triggering, I guess, I think would still exist, but just with this kind of number scale being the thing to trigger that response, and then you'd need a threshold. So yeah, as you were saying, this range is normal, like 0 to 3 is normal, 4 to 6 requires like review in 4 hours, and 6 to 10 requires immediate review, for example.
Yes. Just I'm interested in the actual sort of mechanics of your refill. Did you have somebody who was collecting and collating all of the data? Were you kept separate from that, or were you spending your whole time running around hospitals all over?
I wasn't doing the actual data collection, so we had research midwives who would go and meet with the women in our study and actually collect the data and hand out the kits and get those back. But I was involved in setting up the trial, so like in designing the software that we used in the tablets. I managed the database, so every time a woman submitted her vital sign data at home, it would like in real time be sent back to our servers, and so I'd see that come in. And if there were any mistakes in the data, like if the midwife had accidentally skipped the temperature screen and not entered that, then I would input that back in. So I was involved in maintaining the database and having a say in how the study was run and what devices we used, for example. But I didn't actually do the seeing the woman part.
Probably good design anyway.
Yeah, you kind of need to have a clinician do that part anyway. So,
yeah. And that took you all told to get all those 1,000 cases you had or something?
Yeah, so the trial, the first part of the trial had started before I came on board, and then I helped set up the multi-centre phase, and then I left a year before it ended. So I was involved for 4 years. Yeah.
Did you have much racial variation across all this?
Mainly in the London site was the biggest racial variation. Oxford and Newcastle were primarily white.
Interesting for you to do the same thing here, of course. Sounds like a real HRC winner to me.
Great. If we have no further questions, let's thank Rebecca again for a very interesting talk.
Yeah, thank you very much.
Please join us for some refreshments.
Copyright University of Auckland, all rights reserved. The content and delivery of lectures in this course are protected by copyright. Material belonging to others may have been used in these lectures and copied by and solely for the educational purposes of the university under licence. You may record the lectures for the purposes of private study or research, but you may not sell, alter or further reproduce or distribute any part of these lectures to any other person. Failure to comply with the terms of this warning may expose you to legal action for copyright infringement by the copyright owner and/or disciplinary action by the university.